Okay, let's get started. I think it's time right now. Although this lecture will mostly be a review for most of you, we're going to cover some fundamentals and caches, mainly because you're going to do a cache assignment. Hopefully we'll cover some advanced topics in caches also, although we'll see how long where we get through. And feel free to ask questions, I think, because most of you should really know this material. This is really digital circuits or basic computer architecture material. But before we jump into that, I'll cover some other fundamentals. I like digressing, as you know. It's always good to digress and find some other ideas. But please feel free to participate. So, okay, this is where we left off last time. Last time we had a relatively short lecture, 2 hours. I'll try to keep it to 2 hours. 3 hours is long, but today I don't know. Whenever I say I'll try to keep it short, it usually goes long. So my predictor is exactly the opposite. You'd like to flip the prediction in this case. Okay, why study computer architecture? This should be familiar to some of you, but I think it's important as part of the first classes to motivate ourselves to understand what is the landscape we're working with today in computer architecture. Of course, this is a fascinating field for me, computer architecture. I would study it again and again, over and over. It's very fundamental, I think, because it's really how we build systems and computers. But I think we're especially in a very important time frame in the history of computing to study computer architecture, because a lot of things are changing significantly. It's almost like the 1940s or so when first computer architectures were really designed, because a lot of things are being questioned at the moment. But before that, what is computer architecture? Basically, this is my general definition. We'll change this. We'll distinguish between computer architecture and microarchitecture in a little bit, and we've done that in digital circuits, but this is the general definition. Basically, it's a science and art. We'll see why it's art. I think it's very much art also, in addition to science. Designing, selecting, interconnecting hardware components, and designing the interfaces to create a computing system that meets many, many goals. And we looked at some of the goals in the first lecture. We're going to look at more. Like this is an example interface, right, in an architecture. Is this a good interface? You could always argue. It's a very non-intuitive interface. I was not expecting this, right? I don't know how you guys were expecting that, but that's a programmability problem exactly, right? As a programmer, I'm not expecting this interface, but once I understand this interface, I can do it. It's very specialized. I'm not sure if I can program everything using this, but it's an interface. So somebody designed this based on something, although I'm not sure if they thought about it as much as we think when we design computing systems. And I think as an architect's mindset, it's good to have that mindset. When we design chips, for example, it's very rigorous, and it's good to apply that mindset to other things that we have in the world potentially, so that we can make things more efficient. Like I always have these problems with traffic lights. There's so much time wasted on the road because these traffic lights are extremely inefficient. And sometimes they do exactly what they're supposed to do, right? They turn red when you're the only one and you need to cross the road. Okay, they could be smarter, of course. Yeah. Okay, so enabler has been Moore's law. Many of you know this. I'm not going to go through this in detail. This lecture I'm going to go really fast, I think. I'll try to. Although hopefully my predictor will not go wrong on this one. Otherwise, we'll delay what we're going to cover next time. So this is Moore's law. This is Intel's picture circa 2005. Basically, it says component counts that you can place on a chip double every other year. You could argue with double, because this is really an empirical law, right? It's not a physical law of nature. It's an empirical observation. And transistor counts have been doubling every other year, let's say, approximately. And that has enabled a lot of things in computer architecture. That has enabled us to put a lot of stuff, integrate a lot of stuff on a single chip. And this is actually Moore's first drawing in his paper that basically observed this phenomenon, right? You can see that over the course of years, component counts that you integrate on chip doubles. On board, actually, in that time. And this is another interesting view of that, what he drew in that paper. Basically, this is the number of components per integrated circuit. It's logarithmic scale, as you see. And this is the relative manufacturing cost for a component. It's logarithmic scale. And as time goes by, the Pareto optimal point where the manufacturing cost is minimized moves to the right, meaning that you can put more components on chip because technology improves over time, and that's essentially been known as Moore's law. This is the manufacturing process, and people have kept up with it over time. If you actually extend this curve, you will get something over here perhaps, right? That's why we can manufacture transistors very, very cheaply today. Of course, you can put more components on chip by increasing the wafer size or your die size, right? But that leads to higher manufacturing costs, as you can see over here. You could put less, but that also increased the higher manufacturing costs. And you should really read this paper. It's a beautiful, short, 3-4 page paper. How many people have read this paper? Gordon Moore's paper? Okay, nobody. This is a good assignment then. It's only 4 pages. It's 1965. It's beautifully written. This is Gordon Moore, and the law is continuing, as you can see. And some people say that this is a law of psychology now. Basically, it's really competition because this is an economic argument, as you can see, right? Economically, to minimize the cost, you'd like to be operating at this point. And every year, that point changes. But people also argue that this is a psychological argument because now that this law has been like this for a while, everybody expects that you should really achieve the next curve over here. And people compete, let's say, wherever they manufacture processors. Silicon Valley is a really good example of this place. People compete to achieve that curve. And if you actually fall behind, somebody else is going to achieve that curve, and hence the psychological law. Okay, it's fun to think about it. And this is 2011. So we basically clearly can put right now, more than 3 billion transistors on chip, and it's growing. I don't know the exact counts of the most dense processor today. So what do we use these transistors for? I think your readings for this week should give you an idea. This is a recommended reading. In the past, it was a required reading. I recommend it this time because I want you to read some of the other stuff also. And these are required reviews as part of homework 1. We should really put up homework 1 sometime. So you're going to have fun with some of these papers, I think. But we're going to cover this reading a little bit in this lecture. This is also a recommended reading. Maybe it should be required, but I would definitely ask you to read it. It's fun. It's only 3 pages. And there are nice insights over here. And this is a nice insight. 1975, 65,000 components. We're talking about 3 billion today. That gives you how fast things are growing. And another quote, which I think is forward-looking, is, will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? And this is actually true today. Heat is a big problem in most systems, in high-performance systems. So how to cool those systems is going to be important going into the future. Okay, so what does this enable? Actually, computer architecture is not just about Moore's law. I should mention that. I kind of rode on Moore's law over here because that has been an enabler, but it's not about Moore's law only. Now that we have a lot of transistors, what happens if Moore's law ends? And I believe it's going to end at some point, and some people argue that it's already ended. I don't believe that it's already ended. I think people are still pushing for more transistors on a chip. They may be using them in a different way. Maybe it's slowing down. But if it ends, let's say you cannot put more transistors on chip, actually architecture will become even more important because you're not getting transistors for free. Now you have to be extremely judicious and more efficient in how you use those transistors, right? So you need to actually somehow really bridge the gap between the algorithms and the transistors that you have available to yourself. So there's a lot more to do in architecture. And it's going to become even more important once these scaling, Moore's law scaling really ends, in my opinion. But regardless of whether or not you have Moore's law or you don't have Moore's law continuing, you can use whatever you have to enable better systems. You can make computers faster, cheaper, smaller, more reliable, more secure. By exploiting advanced and changes in the underlying technology and circuits. We talked about the role of the architect looking down, for example, looking at the technology, right? What's happening. So you can exploit those. You can exploit the applications, of course. You can exploit the higher levels. You can enable new applications. And I think a lot of these things that are written over here were not possible in the past. They became possible. For example, visualization became possible with the power of the GPUs and physics processors. And that was enabled because of a lot of architectural improvements, plus technology improvements, of course, right? And I think people are pushing for self-driving cars, personalized genomics, all kinds of interesting stuff. We'll have some guest lectures on genomics, for example, as I mentioned earlier. You can enable better solutions to old problems also, but also new problems. And I think for a long time, software innovation has been built on trends and changes in computer architecture. You get significant performance improvements over time. And software in the past didn't need to change much to exploit those because it was free, essentially. Now maybe we're in a different regime where hardware improvements are getting harder, so you need to actually improve the entire system, perhaps. That's why we're in this era where people are really looking at more specialized solutions. You're seeing a lot of accelerators for very different purposes like machine learning. The general purpose performance improvements is not happening as fast as before, because of what we will discuss in a little bit also, because of complexity, energy, power. But clearly we can enable better solutions by using architectural techniques, whether it's building a much better general purpose processor or building very specialized nice accelerators that you can power on and off at the right time, depending on the application. Those are all architectural solutions in the end. And in order to actually specialize your application to what's the underlying hardware, you really need to know a lot of things across the stack. It's not just architecture, but architecture is really right at the heart of it, if you will. Okay, also understanding why computers work the way they do, I think this is really important. I think this is, as a computer scientist, this is really critical, or computer engineer or electrical engineer. But even beyond that, I think if people understand why computers work the way they do, this could be very useful for the future that's coming for us, for example. Maybe self-driving cars, who knows, robots governing countries, right? It's better to understand, I think. Not just because it's painful to reboot this once in a while, and if you understand, maybe you can do better. I'm not sure. Maybe we're beyond that point. But I think this is really important. Of course, it's a joke. It's always good to understand. Okay, so I think today is a very exciting time to study computer architecture. And industry is in a large paradigm shift to multi-core and beyond. Actually, multi-core has already happened. And clearly, it was not the solution, right? Everybody was thinking in circa 2000 or so, oh, these single-core processors, they're consuming a lot of power. They're not parallel enough. So let's build this multi-core. And clearly, people quickly figured out that that was not the only solution, and that was not necessarily a good solution for everything. As a result, today we don't know what to do, essentially, both in industry as well as research. So there are many different potential system designs that are possible. That's why you're seeing this proliferation of these accelerators, actually. People are building very specialized architectures on FPGAs or ASICs. Really what has motivated this what has motivated this is many difficult problems at different layers. And some of these difficult problems are actually caused by this paradigm shift because we don't know what to do. So clearly, I'll go through this relatively quickly, but we have a huge hunger for data, and there are new data-intensive applications we want to enable. And you need a different paradigm for maybe different applications. We have significant power, energy, and thermal constraints, both on the large scale as well as the small scale. This is very constrained, but also data centers are very constrained, especially if you care about sustainability. If you want to destroy the world, then yeah, maybe you can find solutions, but that's not a good idea, I think, in the long run also. Complexity of design has grown significantly with the number of transistors. What do you do with those transistors? How do automated CAD tools work? How do you actually design a very complicated engine that can get you very high single-thread performance? That has actually motivated the shift to multi-core, I think. Multi-core was mainly, from my point of view, a complexity issue. You couldn't design a processor that could buy you more performance at the simplicity that you used to have. It became too complex to extract higher performance. As a result, people moved into this easier option of, oh, you have simple processors and you replicate them, and the design is now simple. Right? But this is still important because complexity is increasing because of the heterogeneity that we have in the system right now. You have many different types of processors, and that increases system complexity. How do you manage it? That increases the software complexity also. Okay, difficulties in technology scaling. We've talked about Rowhammer. It's a very good example of technology scaling difficulties, but there are other technology scaling difficulties that we didn't talk about, like reliability problems that you have, or one of the benefits that technology scaling has provided us was as you reduce the size of a transistor, you could reduce the voltage, and you could get significant energy efficiency, but that has stopped currently because we're at too small node sizes. This is called Dennard scaling. Bob Dennard is actually the inventor of DRAM, but he's also the inventor of this, maybe not inventor, but the observer of this Dennard scaling law that says as you reduce the size of the transistor, you can reduce the voltage linearly. But now we're in a regime where if we cannot actually reduce the voltage because everything is too small. And you run into a lot of reliability problems if you reduce the voltage. Which means that as you reduce the size of the transistor, you're not getting better energy or reasonable energy scaling. As a result, we have this technology scaling problem, which is compounding the power, energy, and thermal constraints. Okay, I'm giving you a lot of things very quickly, so feel free to stop me if you have questions. But the next one is memory wall and gap, which we're going to talk a lot about. There is a fundamental disconnect between data storage and access and computation today, and that disconnect is growing. Even though processors may not be getting faster, that in the past, processors were getting faster, much faster than DRAM bandwidth was increasing. I think that has changed. Processors are getting not as fast. DRAM is getting faster, but there's still a huge disconnect between memory and processors because we know actually what to do with computation. We can design processors really well. That's not a problem. We can scale them. We have a lot of transistors to put processors on. But memory side, this interconnect is not scaling. In fact, interconnect has been the main bottleneck for a while. Now it's becoming the huge bottleneck. Okay, reliability problems we talked about. Programmability problems. Programmability is always important, right? This, like what I showed you earlier. If you don't know how to program it, you cannot even change this, right? And security and privacy issues like Rowhammer is an example, but there are more, of course. Meltdown and Spectre has been discovered with the mentality of hardware is important. And there's more to come, I think, that's going to happen. And these are difficult problems because Meltdown and Spectre, for example, probably, how many of you know about Meltdown and Spectre? Hopefully, okay, good. So you're following the popular news, at least. Yeah, basically, I think that's very fundamental because that's due to the way things are designed, right? It's a fundamental thing about speculative execution. And that happens in all processors that employ speculative execution and that are good enough to execute things fast, in my opinion. So it's very fundamental. And people always took speculative execution and out-of-order execution and branch prediction for granted to get high performance. And it makes sense because the mindset was, let's get high performance. And that's how you get high performance. But the problem is, now someone has figured out that, oh, that could lead to security problems, right? Now how do you actually design techniques that are fundamentally secure that can get you high performance? I think that's a key challenge going into the future because it's not going to be easy to just go for high performance without considering all of these other issues, security, as an example. Now, that was not true for a long time, actually. People were driving for high performance, but then when power and complexity became a concern, the designs shifted to energy a little bit. High performance was still a key constraint, but energy was also a very key constraint. So people were doing energy-efficient high performance designs, but they were still not taking into account security issues. Now it's very fundamental, I think. So it's very an exciting area because things are getting combined. Because whenever you're designing, you cannot just design for a single metric anymore. You really need to consider many, many things at the same time, which makes it fun, I think. So there are no clear, definitive answers to these problems. So how do you solve these problems requires a lot of architectural thinking and creativity, I think. Now, I guess in today's climate, somebody can say, oh, give it to the machine learning, artificial intelligence, and they will figure it out. But how do you do that is also requires creativity and architectural thinking, right? Because machine learning is not a solution to everything. You have to know exactly how to make it work. Okay, and we're going to talk about how to design components that can actually use machine learning to improve performance, for example. Even for that, you need to know exactly what inputs to provide, what should they examine. We'll later cover, for example, reinforcement learning-based memory controllers, some work that we had done about 10 years ago. So that should be interesting. But it's not easy to get that machine learning to do what you really want. Okay, I spent a long time on that slide. Any questions? So my prediction is already not going well. Okay, basically these problems affect all parts of the computing stack if we don't change the way we design systems. As I showed you with the Rowhammer, that's a very clear example, right? And this is real. It's not, it's real basically. So there are many new demands from the top. This is looking up, the architecture part. Many new issues at the bottom. Architects need to look down. And there are many fast-changing demands and personalities of users. This is also critical, I think. Today, users are a lot more agile with computers, right? 70, 80 years ago, computers were really designed for a very specific set of users, right? After the personal computer in the 1980s, of course, the user space grew significantly. But now, user space is everywhere, right? Everybody is a computer user today. Well, everybody maybe is an overstatement, but most people in the world are computer users. Okay, and there are no clear, well, I said this already. Okay, I said this, basically, I think there are many, many constraints today in technologies and their issues. There are also emerging technologies that we didn't have that on that slide, but that's also important to see. Like if Moore's law ends, maybe we should switch to a fundamentally different technology, right, that can scale better. Today, we're using CMOS, and that may not be scaling well, but maybe there's a fundamentally different technology. I don't know. People are looking into carbon nanotubes, for example. That could be a technology. Some fundamentally different memory technologies, resistive technologies, that could be better, but we don't know yet. And we're going to cover some of those in this course. And yeah, basically a lot of things are changing today. Whereas if you go back, let's say, in the 1990s, the paradigm was clear, basically. People should design superscalar out-of-order execution processors and make them better, okay, let's say more efficient as well. Those constraints came in the late 1990s. But the paradigm was clear. Everybody should design those, and that's really the dominant thing. There are no GPUs in the landscape. There are no FPGAs. Actually, they are in the landscape, but they're really on the fringes, right? People were using FPGAs, but they were not taking us seriously at that time because the paradigm was very clear, and you could actually scale very well with single-core, superscalar, out-of-order processors with a lot of embellishments, sophisticated branch prediction. But today, it's very different. Today, clearly, that's important also. Making it more efficient is important, those single-core designs. And we covered a lot of that in digital circuits, as you know. So hopefully, you have a good idea of how a single-core processor works today. But there's a lot more today. And basically, today, every component and its interfaces, as well as entire system designs, are being re-examined. In the past, it was basically a simple processor core over here. Even the memory system was mostly ignored, except for caches. Today, we have heterogeneous processors and accelerators, multiple of them. We're connecting them. Hybrid memories, different types of memories. GPUs already have, for example, high bandwidth memory as well as more low bandwidth, higher capacity memory. More general purpose GPUs. This could be a misnomer, of course, right? What a general purpose GPUs means. But GPUs executing many, many more programs today than imagined in the past. Persistent memory and storage. So there's a lot more that's changing over here. And we're going to cover a lot of these in this course, actually. We're going to look at heterogeneity quite a bit because that's one way of getting high performance as well as high energy efficiency. And also different kinds of trade-offs you can enable that way. So basically, the takeaway points, you can revolutionize the way computers are built if you understand both the hardware and the software and change it accordingly today. And I think this is very important today. We can invent new paradigms for computation, communication, and storage. We don't have to be limited to what has been invented. And this is a recommended book that I give. I used to give this as prizes for my for the best projects in the past. Maybe we should start doing that again. Although, do you guys like reading books? How many people like reading books here? Okay, people are honest. Some people say, oh, maybe. That's good. Yeah, it's a different world today, I think. Maybe books should be sent as tweets once in a while. you get some paragraphs from Thomas Kuhn and tweet them out, and I think that's happening. Maybe not the entire books, but yeah. Anyway, going back to the topic, this is actually one of the very high impact works in the theory of science and history of science, actually. Basically, Thomas Kuhn examined how science happens and how scientific revolutions happen, and he was interested in the big ideas that change the paradigms. And he basically says there are three periods in science. One is pre-paradigm. There's no clear consensus in the field. So people actually are exploring a lot of things to figure out, oh, okay, this is the explanation for this phenomenon, right? Light, for example, how does that work? Of course, he's looking at examples in science, but I think engineering is similar. Like today, we're in pre-paradigm science that's trying to find a revolution, I think. There's no clear consensus in the field as to how we build the best processors, right? That may depend on the application. So there's no clear paradigm, basically. We cannot say single core, out of order, superscalar processor with sophisticated bells and whistles is the paradigm. That's not true anymore. But it was true 20 years ago, in the 1990s. There was a dominant theory that's used to explain and improve things. It's called business as usual. And exceptions were considered anomalies, meaning, okay, this general purpose processor can execute everything really nice, so we're going to keep doing that. Or there are these exceptional workloads that fit, like graphics, that fit nicely some other paradigms, but we're going to ignore them. Today, we are not doing that because those exceptional workloads have become the norm almost. There's graphics and vision everywhere, and the GPUs have gotten better executing many, many other applications. So we're not in that dominant theory mode anymore, as we discussed. So we may be actually somewhere in this mode and pre-paradigm science node. We're really examining the underlying assumptions. Are we really building the systems correctly, given the different constraints and given the different applications? So that's why I think it's really exciting. We can actually come up with a revolution or a new paradigm that could change how we design systems. And that could have a huge, long-lasting impact on computing. And also human life, because I think computing is one of the very few things that is really completely integrated with human life today. Even if you want to escape it, it's very difficult to escape, I think. You can argue that there's, of course, an ethical part of this, which we're not going to cover in this course, but for better or worse, that's the case today. That's where we came to. And changing that completely is another different revolution, perhaps, maybe a different paradigm shift. Okay, and that's Thomas Kuhn. So if you have time, I would definitely recommend reading this. It's not an easy reading, but it has a lot of really beautiful examples from real. Of course, he's more examining hard sciences like physics and biology. So there are more examples in that domain. And this is the book. And you can read on Kindle also. This is probably more friendly. So do people use Kindle or this sort of stuff, iPad, whatever? So use that more in general for reading books? Maybe. Yeah, I see more hands right now. Yeah. But I like my idea of tweets also. Maybe we can tweet some of these books. Okay, so the takeaway is it's an exciting time to be understanding and designing computing architectures, and that's what this course is all about. There are many challenging and exciting problems in platform design that no one has tackled or even thought about before. I can give you many examples from memory. I didn't even talk about memory over here, right? There's a business as usual in memory space today, and that business as usual is still continuing, actually. But there's a lot of exceptions that are really shaking the memory space also. That's why memory space is also changing. And that business as usual, in my opinion, is going to get destroyed within the course of 5 to 10 years at most. So we'll see a lot of changes in the memory space. And we're going to cover a lot of the memory space soon. And I said this already before. You can have these problems can have huge impact on the world's future in a good way or a bad way. It depends on the designs, right? And this is driven by huge hunger for data, new applications, even greater realism, as we discussed. And we can easily collect more data than we can analyze and understand today. That's true in genomics, for example. But that's true everywhere. You could argue that some of the data we collect is useless. But how do you figure out useful from the useless is another problem. And it's another computational problem, actually. And as I said, there's also, these are the top-down drivers, application level, problem level drivers. And there are also bottom-up drivers that are causing significant difficulties with keeping up with the top-down drivers. So we have these, what people call walls, and apparently that's not 3. It used to be 3, but whenever I updated this part, I forgot to keep this coherent, as you can see. So there are 5 of them that are listed over here. Energy, reliability, complexity, security, scalability. But first, of course, we need to understand the fundamentals, and this course is all about fundamentals and recent research. So we're going to talk about some fundamentals. And I think this, I really believe in this. You can really change the world only if you understand it well enough. Otherwise, you have to be really lucky. Especially the past and present dominant paradigms, their advantages and shortcomings, trade-offs, and what remains fundamental across generations. I think this is really important. And what techniques you can use and develop to solve problems. So we're going to switch to some fundamental concepts. I'll go through some of the things briefly. Some of these things will be review from digital circuits. But maybe I'll take some questions if you have any so far. Everybody agrees with what I said? Sounds good? Sounds exciting? You don't have to agree as long as it's exciting. Okay, so let's cover some fundamentals. And I'm going to go through this relatively quickly. I'm going to assume that you know a lot of this anyway, but I think it's good to do that at the beginning of the course to put things in perspective. So a computer has 3 key components: computation, communication, and storage. And we're going to cover a lot of it. This is another look at it: computation, communication, and storage. Well, yeah, it's computation, communication, and storage. It's put in a weird way over here. But we will cover all components with a focus on memory and I/O, and a lot about memory and storage in this case. But we will cover interconnects, for example. We will cover processing also, but we will cover more on the parallel processing side in this course. Digital circuits covered a lot of processing in the single core processor design space. And also we looked at GPUs as well. We're going to look at GPUs a little bit more here also. We started memory a little bit in the digital circuits. Now we're going to expand on memory, because this is really one of, I would say this is the major bottleneck that we have today. Okay, von Neumann model in architecture. How many people know about the von Neumann model? Okay, that's good. So you can tell me the 2 key properties then. You didn't expect this coming, maybe. Anybody? Yes, please.
Sequential computation.
Yes.
And memory data and instruction memory are make. Yeah.
Okay, that's good. You had the same?
Yeah.
Okay, basically, yeah, it's sequential instruction processing and a stored program computer. Program is stored somewhere. Okay, basically, memory is unified between instructions and data, as you said. Instructions are stored in a linear memory array, and the interpretation of a stored value depends on the control signals, as we've seen in digital circuits, and you can cover digital circuits for this. The other really interesting part is the sequential instruction processing. Well, okay, I'll ignore that question over here, but a value is interpreted as an instruction whenever you fetch it, right, when the program counter points to it. Otherwise, it's interpreted as something else when you actually try to fetch the data. Sequential instruction processing is a really hallmark of von Neumann architecture, and that's really enabled a lot of development because that has enabled a lot of programmers to get their heads around programming these systems because it's really easy to reason about. Basically, the reasoning is one instruction is processed at a time. That's it. It's fetched, executed, and completed. And the next instruction starts only after this instruction is done. So this naturally imposes a control flow on the instructions. So you have a program counter or an instruction pointer that identifies the current instruction, and that is advanced sequentially from one instruction to the next, unless this instruction changes the control flow explicitly with an explicit control flow instruction, like a branch or jump. Well, jump is a special type of branch, of course. There are many types of branches. Okay, so this is the hallmark, and that's been good for a long time. And these were the readings that I mentioned. Actually, this was a required reading at that time, but this is von Neumann's original paper with his colleagues that talked about this paradigm and the design of a computer. Okay, so you'll remember that. And this is what it looks like, basically. You have this control unit that's the master of everything. You have this instruction pointer that really orchestrates the processing, right? And you have the input and output and memory over here. Okay. So the first question, it's always good to ask these questions if you want to change the paradigm, right? Is this the only way that a computer can operate? And I asked this question in digital circuits, and your answer should be no over here. Because there are many, many different paradigms today that we know of. But a qualified answer is no, but it's been the dominant way for a long time, actually. And it still is the dominant way. We actually use the von Neumann architectures to build multiprocessors, for example. Multiprocessors, really, each processor obeys the von Neumann architecture, but then when they communicate, there's a problem because von Neumann architecture has no idea about what happens when multiprocessors communicate, right? It's not specified. The ordering is not specified, and we're going to talk about that when we cover multiprocessors. But it's the dominant paradigm for a single processor design for n decades, where n is greater than 60, actually 70 now. Well, no, 70 decades, that doesn't work, so n is greater than 7. 6, yeah, there you go. Conversion issues, very important. Okay, so the Dataflow model, this is another model, and this is actually has become very, very popular more recently, especially with the growth of reconfigurable architectures, because they are essentially architectures that do not have this sequential programming model, sequential instruction processing. They don't even have instructions, right? You basically directly map your program into a reconfigurable array of whatever you have, computation units and memories and interconnects, right? And that fundamentally requires a different paradigm to actually program in that case. And Dataflow has been a good model for it. Basically, you figure out the Dataflow graph of your program, for example, and you map it onto this FPGA, reconfigurable fabric. And FPGAs are a very good fabric to enable this sort of Dataflow model, for example. Okay, what is a Dataflow model? Von Neumann model says an instruction is fetched and decoded and executed in control flow order as specified by the instruction pointer, unless you're changing the control flow with a branch, for example, or a control flow instruction. Dataflow model is completely, I don't want to say opposite, but it's a different order. And the order is not sequential. It's the order of the flow of data. An instruction is fetched and executed in Dataflow order, which means that when it's operands, data operands are ready. If it needs one operand, it becomes ready when that operand is ready. If an instruction needs two operands, the instruction becomes ready when both of its operands are ready. And when both of its operands are ready, the instruction is ready to execute, so it fires. And fundamentally, there's no need for an instruction pointer in this case. There's no need to say, oh, I'm executing this instruction, because actually you're not executing that instruction. Maybe you're executing many instructions at the same time, if you do it ideally, right? Because many instructions can have operands ready at the same time if you have this sort of model. So fundamentally, this is much more parallel, as you can see, right? So instruction ordering, in this case, is specified by data flow dependence. Each instruction specifies who or which other instruction should receive the result. And an instruction can fire whenever all operands are received, meaning they're ready. So that's the idea. Potentially many instructions can execute at the same time because you're really not constrained. You're really not artificially constraining things as I'm executing this instruction, I cannot execute the next until I finish this one. And the next one is the next sequential one in order. This could be anything now. So inherently more parallel, as I said. So let's take a look at this in a little bit more detail. So this is a sequential program. You don't need to think about what it does, but it does something, as you can see, some arithmetic operations. Basically, it generates V, W, and then uses them to generate X, and then uses them to generate Y, and then uses those results to generate Z. What is the significance of the program order over here? It's not clear. If in the end what you care about is getting to some result at the end, maybe you don't really care about the program order in this case, right? Program order is significant for debugging, for example, as we've discussed in digital circuits. You have, at any point in time, there's an interface that says, you're guaranteed that the computer should obey the von Neumann model, meaning if you stop the program at any given point in time, there is no inconsistency, meaning that the point you stopped, you could debug it easily because you could stop at this instruction or at this instruction or at this instruction, but you never have the case that whenever you stop the program, this instruction is executed and this instruction is executed, or whatever instruction is executed, but something in between did not execute. You have a precise state. You stop the program here, you're guaranteed that every instruction before that is executed and no instruction after that has started, affected the state. Right? That's the beauty of the program order in this case. But other than that, if you want to get work done and if you don't care about stopping the program, and if you don't have exceptions, it doesn't matter, right? What is the significance of the storage locations? I think this is also important. For example, we add A and B here and store it in V. Let's say it goes to a register. We multiply B by 2 and store it in W. W goes to a register. Now we use V and W to calculate X and Y. And then we multiply X and Y and produce Z. Let's assume we don't use V and W for anything else. What is the significance of putting them in a register? There's no need to put them in a register, right? Because really what you're doing is you're trying to communicate the value that is generated by this instruction to this instruction over here. Same here, and same there, right? Basically, there may not be any need for registers in this case. So the storage locations are enabling you to communicate between instructions. And if you have an instruction-centric point of view, there are storage locations. If you have a data-centric point of view, more data flow point of view, there are values that are communicated. Right? And that's the difference, I think. The mindset is the difference between sequential and data flow. And if you draw this in data flow, this is what you get, basically. I don't put these operations over here, but now you can visualize it because data is flowing in some way between these instructions. And all you want to do is really enable that flow of data and execution of instructions when the operands are ready. And now you can map this nicely to a substrate that can enable you to flexibly instantiate each of these operations and the connections. And a reconfigurable logic, like an FPGA, is an example of that, right? You can map this nicely to an FPGA, assuming that each of the blocks enables you to do these connections nicely at this fine grain. So that's the beauty of the model. That's why data flow has been very important for programming FPGAs today. Okay, which model is more natural to you as a programmer? Let's take this vote. Who says sequential is more natural to me? Okay. Who says data flow is more natural to me? Oh, am I the only one? Oh, okay, one more. That's good. Maybe you're scared. Yeah, I think it depends also. So this question is very interesting, I think, because, yes?
But isn't it basically like people program sequentially and then the compiler translate it into data flow anyway?
That's a good question, yeah. Can it always translate it to data flow is one question, I think. For this program, I think so, yes. For this program, it's possible. But for many programs, it may not be that easy. But I think you have a very good point. There's a higher level translation that you could do from the sequential program into the data flow program also. You may not be able to do it extremely efficiently sometimes, because if people actually said, oh, this is the destination, that's a lot easier. But once you actually have a programming language that's more general purpose, like with pointers and stuff, it becomes very difficult to analyze the program. But I think you have a very good point. It's possible to go between these paradigms, even from the data flow the other way around also, right, by imposing some ordering constraints. The key question is, I think, can you do it for all programs that way, and can you do it efficiently? In fact, people have tried to go from C to gates through a data flow implementations for a long time. You write in C, and then that gets instantiated directly in FPGA. I think that's what you're envisioning, maybe also, maybe not C or Java. Pick whatever your language you love, Eiffel, Pascal. I like Pascal a lot also. How do you, can you do that efficiently is a key question. And there are no really efficient compilers that enable that very well. But I think there needs to be more research in that area also. So in the past, it was a niche area. I think currently it needs to be a more mainstream area to do research. Okay, I think this question is interesting also because of education potentially, right? Because most people programmed through this, I assume, when you learned programming. You didn't program in this. Has anyone programmed in Dataflow? Okay, so it fits naturally to you because maybe you're more familiar with it. So there's also an educational aspect to it also. It's not clear if this is really fundamentally because of the way humans are built. I don't believe so, actually. I don't believe humans are built sequentially. We're educated that way, maybe because we want to make sense out of the world. Because the sequential paradigm is very much true in the world also, right? You usually do one task at a time. You don't do 200 tasks at a time. Although some people are good at doing 200 tasks at a time. Maybe 200 is an exaggeration. So it's not, maybe it's not fundamentally sequential, but we impose that sequentiality in a lot of things in life as well. So there's a bigger interface here than the ISA interface. Okay, so more on data flow. Actually, I have more lectures on this, and you've seen this actually in digital circuits if you've taken. But I think this is really interesting. In a data flow machine, a program consists of data flow nodes, and a data flow node fires. It's fetched and executed when all of its inputs are ready. Now, we're not talking about mapping the data flow graph onto a reconfigurable architecture. I think that's really interesting. But we're talking about changing the instruction set architecture of a general purpose machine. People have tried this a lot. It's not an easy thing to do. So this is a data flow node, and you represent it as an ISA instruction in the instruction set architecture. This is an example, right? You have this multiply. You have the ready bits for argument 1, ready bit for argument 2, and this is the destination of result. What does that mean? This is the address of the instruction that's going to get this arc, that's going to be connected to that arc. And you can actually construct programs this way. You can turn this data flow graph into a set of instructions that you can fetch and execute, except you don't specify an order. The order is specified by when the data is available on these arcs. As you can see, these ready bits enable tracking of whether the data is available. So if you receive a result from some other instruction whose destination is this instruction, and the destination also specifies which arc, is it the left arc or the right arc, then this becomes ready. And if later you receive a result from another instruction whose destination is the right arc of this instruction, this becomes ready. And there needs to be some logic that detects that both of these are ready and fires, meaning fetches and executes this instruction, and then generates the result, and the results get routed to the destination instruction. So that's the operation model of if you want to do a general purpose system with an ISA this way. With an FPGA, it's completely different. You don't really need to turn this into an instruction, right? With an FPGA, you just go and somehow make sure the connections are switched correctly such that this node gets connected to this other node, and then you instantiate an adder over here and then ensure the flow of data. Of course, if your data flow graph is much bigger than your FPGA, you have a problem, right? Or if you have constraints in your FPGA, then it becomes a problem. So you need to handle all of these real-world ugly cases, and the real world is not that nice. Okay, but this is the data if you want to turn it into an ISA. And you can actually construct an ISA, a very general purpose ISA, that can do anything, basically. This is a Turing complete, as long as you specify these things. Well, not all of these, but these are examples, actually. This is a conditional node, for example. Basically, it has two inputs, the data input and the control input. And basically, the semantics is that whenever you have tokens, these are called tokens, these red things, or inputs, but let's call them tokens. Whenever you have tokens in both of your input arcs, data and control, this instruction fires. And what does it mean? The firing means that you take the data input and pass it to the output, data output that's specified by the control input. So in this case, it says false. False means that this node should pass the input data through the false output. That's the idea. If this was true, you would basically send the data through this out. That way you can select now, right? You can select where you route the token. For example, if a condition is false, then you route the token to an addition operation over here. Otherwise, you route it to a subtraction operation, for example. That's an example. Okay, so you need to, of course, compute conditions as well. So you need relational nodes that look like this. And this is very simple, as you can see. It fires when both of its inputs are ready. And it basically computes whether the left input is greater than the right input. And if that's true, then it sends a true token out. Otherwise, it sends a false token out. And that's how you connect. Now you can connect this and this to something else. And you can actually have arbitrarily complex nodes. This is an example of barrier synchronization. You guys know about barrier synchronization? Anybody? Okay, maybe. So the idea over here is basically you want to synchronize multiple streams of computation before you move on to do something else with the data. Right? That's the idea. If you want to do that, basically you create a node that looks like this. Let's say you want to synchronize 3 different things. 3 different loop iterations, let's say. They all produce some output, and eventually you're going to merge that output somehow. Basically, you wait until all tokens are ready, and once all tokens are ready, you pass the outputs to the next stage. So this way you synchronize, you ensure that no output is sent to the next stage of computation until all of the outputs are ready, or all of the inputs are ready. Does that make sense? Yes?
So the next step of computation will wait for input anyway. What does the barrier
next stage of computation will wait for the input anyway. Well, it depends on what you have over here, right? If you already passed this. So here, in this case, you're guaranteeing that you're sending all of the 3 outputs at the same time. Does that make sense?
I understand what it brings more, but I don't know how it will be useful later, since the next step of computation will anyway need all 3, so it would have waited.
Oh, maybe it doesn't need all of the 3. Okay. Maybe it needs 1, right? Maybe it needs 2 out of the 3, right? And you really need consistency on all of them. Does that make sense? Yeah. So it really depends on the nature of computation. I understand your question better, yeah. If it needs all 3, yes, sure. Okay, I need to change my batteries. Any other questions? So and one example of this is, for example, if you're counting the words in a book, let's say, or the number of letters, different letters that you encounter in a book. You're creating a histogram of the number of letters. And you can partition this book into, let's say it's a 1,000-page book. You partition it into 100 threads. And each thread picks 10 pages. And it counts the letters in its 10 pages. And there's some computation that you do at the end on them. Basically, you merge these results. So in order to be able to merge those results, you need to wait until all those threads generate the results. Of course, you could optimize this. There are ways of optimizing this, but this is one way. And this is a very common way of programming parallel machines. This is also called the bulk synchronous programming model. Leslie Valiant is the inventor of this. Basically, you partition your parallel program into pieces. You partition your data, let's say, into n pieces. And n threads operate in parallel completely. They don't synchronize. But at the end of what they do, they synchronize. Now you can use the results for something else. And you assume that results are consistent at that point, as if only one thread operated on all of them. Yes?
But I don't quite understand this. If you draw your Dataflow model, and you implicitly assume that every node only executes when it has the necessary inputs, why would you ever need to draw one of these barriers? Because the nodes work this way anyways. So if you merge your results at the end, you will have some configuration of nodes that will only execute when the results.
That's a very good question. I think maybe in some cases you don't need it, but let's assume that you want to expose some of the results to the user. And the user wants to see everything at the same time. I'm not sure about this. I haven't thought about it yet, but I think that's a very good question.
Yeah, but then you might just have like one node that prints the result out to the user or something.
I guess that's true. It depends on the complexity of the nodes also, yes. Maybe you don't need it if your nodes are complex enough. Yeah, if you, but usually you don't have nodes a lot that are connecting a lot of data. But this is a good point. I think this is something to think about for sure. Usually these interactions are needed whenever you're synchronizing with different programs. And they may not really, and you depend on the user input, and the latencies are not predictable. But maybe there are ways of getting around that, because this is really not fundamental in the end, right? This is all you need. All you need is really maybe and or not, right? That's the Turing complete. So I think we're getting back to that at this point. What is Turing complete? You just need an and. And with an and, you do everything. But it may not be very efficient to do that. Is that clear? I hope that's a satisfying answer, because with an and, you can build anything in the end. OK, good. So this is an example Dataflow program. I'm not going to go through this, but you can study it. We did it actually in digital circuits. Does anybody remember what this does, or does anybody know what this does magically, very quickly? OK, maybe you can think about it a little bit. Yes?
It computes the factorial of the input.
That's right. It computes the factorial of the input, basically. It's n factorial over here. Of course, you need to have some assumptions. N is non-negative, right? If you start with n negative, then I don't know what this does. It probably doesn't terminate. But basically, yeah, that's it. It computes the factorial of the input. And you can actually convince yourself by studying it afterwards. This may not be the best way of implementing n factorial in Dataflow, because it's really very sequential, actually, if you look at this. You may want to parallelize it somehow, but we're not going to go into that. But this basically shows that how Dataflow operates. You have an input n, and you have an input 1 over here. I didn't specify that, sorry. But basically what happens is you get n. This fires when the input is ready, and it copies the n. So this becomes n, and this becomes n. Now this fires because it has only one input and input is ready. It checks if n is greater than 0. Assume that we have n greater than 0. So it copies this node again. This produces a true. Now this is true and this is true. And we had n over here. So we had n and true over here, which means that n passes over here. And n gets copied again. This is n and this is n. And in parallel, something else happening. One is here, and this is true, as you can see. So 1 goes over here, and we have 1 here, n here. So we multiplied 1 and n. And that gets fed back to this input over here. So there's something that I ignore over here. Basically, initially this is 1, but in the next token that comes over here will be n. And the next token that goes over here will be n minus 1, right? Now you do the same thing. So previously we multiplied 1 by n, this input by this input. Now we have n minus 1 over here, sorry, n over here and n minus 1 over here. So multiply n by n minus 1. If you keep doing that, you will see that the next time we'll multiply n times n minus 1 with n minus 2, and that's n factorial. It may not be the best way, as I said. It's very sequential, as you can see. But this is a Dataflow program with some assumptions that does this. OK. So basically, this is an ISA level trade-off. Do we need an instruction pointer in the ISA? That's a key trade-off in an ISA. If your answer is yes, you're control-driven and sequential. An instruction is executed when the instruction pointer points to it. An IP automatically changes sequentially. If your answer is no, you're data-driven and parallel. I'm not sure if that's the only space of the no answer, because this is one example of a no answer. An instruction is executed when all its operand values are available. This is called Dataflow. And there are many trade-offs that now this enables, right? Many high-level ones. Ease of programming for average programmers. You mentioned that that may not be a problem if you still program the same way and something else translates it for you. But is it then the question is efficiency in terms of performance, in terms of energy, ease of compilation, which one's easier, depending on what you want to do, hardware complexity. There are many, many issues over here, right, that we're not going to cover. A similar trade-off actually exists at the microarchitecture level. Basically, we discussed ISA versus microarchitecture. I'm going to talk about that a little bit more. ISA specifies how the programmer sees instructions to be executed, whereas microarchitecture is how the underlying implementation actually executes instructions. Right. In the microarchitecture, you don't need to obey the ISA as long as you keep the contract. Right. This is a contract. So ISA may say programmer should see a von Neumann model, or programmer should see a Dataflow model. Microarchitecture can do something completely different underneath. Right? It can execute instructions in any order as long as it obeys the semantics specified by the ISA when making the instruction results visible to the software. Right? So programmer should see the order specified by the ISA in this case. So you have a lot of freedom at the lower level. This is the beauty of operating at the lower level. And we've seen this a lot, right? Basically, you may have a control flow model, von Neumann model, but most high-performance computers today don't obey that at the microarchitecture level, right? What they do is they actually have a restricted data flow model. They convert those instructions internally into a data flow graph representation, and then they execute instructions in the data flow order inside the machine. And they can actually do it for 256 or more instructions today. And it's growing. Of course, this costs a lot of complexity because now you need to convert the sequential instruction representation into a data flow graph representation internally and store it and then make sure all of that machinery is satisfied. But now you get some of the benefits of data flow. It's not complete data flow. That's why it's called restricted data flow, because you see only that part of the data flow graph that you keep inside the machine. And if you can keep 256 instructions, you can only construct a data flow graph from those 256 instructions. So you see only the partial data flow graph of the program, not the entire data flow graph. But it's beautiful, I think. And this worked really well. So the ISA level data flow, there was a lot of research on it, starting from this paper, actually, 1974, the seminal paper by Jack Dennis and Misunas, in ISCA 1, I think, or ISCA 2. This is the Computer Architecture Conference, one of the major ones. There was a lot of research from 70s to even 2000s that talked about data flow, but it was very difficult to get the software infrastructure to actually be data flow. Today, I think it's easier because of FPGAs, for example. But at that time, the paradigm was, if you think about it, it's very single core, sequential. So that paradigm actually engulfed the data flow paradigm, if you will. Right? What happened was you couldn't change the ISA to be data flow, but internally, you could change the microarchitecture to be data flow. As a result, you got the benefits of the data flow while keeping the interface sequential. But of course, the benefits may not be as high as what you would do with a pure data flow machine, right? So it's a trade-off. So the trade-off is you keep the programmer sane because the programmer is used to sequential execution, but underneath you do something completely different. And I think this is a very good principle. If you can do that and if you can be efficient without while ensuring the software infrastructure doesn't change at all, that's great, right? And that's why this model of out-of-order execution restricted data flow in the microarchitecture has been very, very successful for 30 years or so. In fact, I've invited one of the big proponents and big leaders in data flow, Arvind from MIT, who is going to give a distinguished lecture on November 26th at ETH. I think you guys should definitely go to his lecture. He's not going to talk about data flow as far as I know. He's going to talk about some other things, but I'm sure he will touch into data flow. But he's done a lot of work on data flow, and he had a keynote talk at ISCA in 2005, and he said that why did data flow as an ISA paradigm not take off? We did all this research, but as an ISA paradigm, it didn't really take off. It impacted the underlying levels, but not the higher levels, because he said we should have spent more time on software. Basically, we should have spent more time on actually porting the software and showing how you could actually do the software on these machines. And that was really the limiting factor. And I'm not sure personally if that would have actually taken off because the paradigm was very different at that time. But today, I think data flow is a lot more fit for the paradigms that we have. So that's why it's very, very interesting to look at. If you're really impatient about this, I have a much more detailed coverage of Dataflow in an earlier lecture. This is from 2013. I covered it last year in digital circuits, but it was also high level. But this goes into details of some of the Dataflow machines that were built, for example, at MIT and Manchester at the time. And there were a lot of other machines that were built in Japan, for example, but none of them actually really took off, interestingly. Okay, I'm going to take a break after this, maybe. So all major instructions that are actually after these set of slides, and then I'm going to give you a long break, and then we'll decide what to do afterwards, since I'm taking too long, as you can see. But hopefully this is interesting. Is it? Am I going too slowly, you think, or are these stories good? Okay. Maybe you'll study caches on your own then. Okay, well, who knows about caches? Let me ask that question first. Okay, we should probably study a little bit. Who doesn't know anything about caches? Who is ambivalent about their knowledge? Okay, a lot of people. Okay, we'll cover caches, but quickly. Okay, so today's all major instruction-set architectures today use the von Neumann model. Underneath, implementations are very different, as I said. They use pipeline instruction execution, multiple instructions at a time, out-of-order execution, separate instructions in the data. Basically, they violate everything that von Neumann architecture specifies, right? Basically, what happens underneath that is not consistent with the von Neumann model is not exposed to software. That's why they can violate everything underneath, right? This is the difference between ISA and the microarchitecture. And this is more said in a longer way. This is my definition. This is a traditional ISA-only definition by Gene Amdahl. You probably know Amdahl's law. He was a designer of IBM 36091, which is one of the first out-of-order machines. And basically, he says the term architecture here is used to describe the attributes of a system as seen by the programmer. In other words, the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. So basically, ISA is what's seen by the programmer. Everything else, it's distinct from what goes on underneath. Right? It's a contract, basically. So basically, this is the agreed upon interface between software and hardware. Software and compiler assumes, hardware promises this. I think of this as what the software writer needs to know to write and debug system and user programs. Microarchitecture is a specific implementation of the ISA. Oh, I should probably put that over there. It's not visible to the software. And a microprocessor is ISA, microarchitecture, and circuits. Basically, whatever is underneath over here. And architecture usually is used today in a sloppy way, fuzzy way. It's really ISA and microarchitecture together. If someone says architecture, usually they mean ISA and microarchitecture. They may sometimes mean microarchitecture. They may sometimes mean ISA. But it's really used in a not so well-defined. That's what I mean. What I mean by sloppy. It's not so well-defined way. But if you really want to define what ISA is, that's different from microarchitecture. Okay, so let's. I'll finish these slides and then we'll take a break, and then we'll do the caches. So what is part of ISA versus microarchitecture? Basically, it's the interface. I think of cars. And as a cars, you have the gas pedal. That's the interface for acceleration, right? And that's a very common interface across cars. That's not the only interface, but that's a very common interface. Everybody has adopted that interface somehow. But underneath, how you implement acceleration is very different from car to car, right? Hopefully that's clear. I'm not going to go into the details of the car. And implementation of the microarchitecture can be various as long as it satisfies the specification of ISA, even at the level of an add instruction, for example. How do you do an add? An add instruction says you add these two values. Even that specification can change, of course, right? You add these two values in these two registers or memory locations and put the result in this register or memory location. As long as you obey that, you could design your adder in any way, right? You could design a bit serial adder. What does this mean? You take the registers bit by bit, add the first bits, generate the value, and generate the carry, and now add the second bits. You do 1 bit addition per cycle until you add the full 32-bit value. That's called bit serial addition. It has a lot of benefits, right? It's very small, compact, because you just need a single bit adder, and you use it over, let's say, 32 cycles if you're doing the addition in one cycle, and if you have 32 bits to add in the values, the latency is long. The trade-off is different now, right? It's very energy efficient probably for that particular bitwise addition. It's very area efficient, but the latency is long. But it may make sense to implement something like this if you're doing a lot of additions, right? If you're doing millions and millions of additions, but you don't care about the latency of each addition that much, 32 cycles, who cares, right? Maybe, right? If you're, for example, updating the huge picture, million by million pixels, and you're adding something to those pixels, doing some operation on them, maybe you don't care about the latency as long as you meet the deadline, meaning user is not going to be upset as long as you actually refresh the frames at the right rate, right? And 32 cycles are not going to matter for the user. I can guarantee you that, unless your cycle time is huge, of course, right? There's always a caveat. But in today's cycle times, it doesn't matter. So bit serial addition actually can be very, very interesting if you're doing many additions. So we may cover the connection machine. This connection machine was designed in the 1990s to do large-scale computation. And it had actually 64,000 bit serial adders. And they wanted to do parallel computation. We'll talk about that maybe when we talk about interconnects, because they had very interesting interconnects also. Of course, you can do ripple carry addition. Have you guys studied adders? In digital circuits, we covered them, but we didn't go into a lot of detail, of course. Yeah, some of you. Who hasn't studied adders in the past? Don't be afraid. Good. Okay. Okay. Who doesn't know if they studied adders? Okay, that's also good to know, right? A good chunk of what's important is you should know what you don't know, right? Okay, I think ripple carry adder is another example. Basically, you don't do a single bit, but you do multiple bits. But what you do is your critical path is determined by how fast the carry propagation, basically. You generate a carry, and the next bit the computation can start only after you generate this carry, and the next bit computation can start only after you generate this carry, ... So it's slow, basically. But it's not as slow as a ripple carry adder. It's not as slow as a bit serial adder. Now people have designed many, many other adders like carry look ahead that try to parallelize the computation, assuming some carry. So clearly there's a huge trade-off between these different adders, even if you look at a simple thing as an adder, right? And this is all microarchitecture of the adder, basically. It's not, you don't expose the carry look ahead behavior or ripple carry behavior or bit serial behavior. The user just is an add, and the add happens. Similarly, the add may happen inside the memory engine with DRAM, right? DRAM does some kind of addition, which we will talk about later on. And the user has no idea about it, as long as that happens. It could be done through an analog circuit, if you will, right? It doesn't even need to be digital like this. Again, that's microarchitecture underneath. So x86 ISA has been a very successful ISA and has many implementations. Let's go to another level. x86 ISA at the ISA level, not an add instruction level. But ISA has many, many implementations, and clearly I've stopped updating my slide after some point over here, which is as expected. Yeah, I don't know what Intel calls. Intel doesn't even specify these. I think they become very fine-grained right now, like this Kaby Lake, Coffee Lake, whatever those are, those different lakes, rivers. Yeah, and I think code names have also become the real names these days. It's kind of weird. Okay, so as a result of this, microarchitecture usually changes faster than ISA, actually. Well, as a result of the fact that you don't expose it to the software. Right? If you expose it to the software, you cannot easily change the ISA, because people have written a lot of software. They're used to writing the software. If you change the ISA on them now, their program will not run. Or you need to change the ISA in a way past programs run, and you add some new things, but that's not as easy. That increases the complexity in the system. That's called backward compatibility, right? The previously written programs run on the new ISA, but people can write new programs with new instructions that are added. But now that increases the complexity, and x86 has done that a lot over time. That's why it's a very complicated ISA right now. Over time, it's added a lot of new things like that, while keeping the backward compatibility. For example, it has different very different instructions, like string compare, string move. Actually, those are used. But they're also not so used instructions, at least in the common case, because you never know what's used and what's not used until you break the ISA and that program doesn't run, and your customer comes to you saying that my program doesn't run anymore. Right? Yeah, basically, for example, there are data types like binary coded decimal that is hard-coded into the x86 ISA as a data type. Not many people use binary coded decimal today. So yeah, so microarchitecture can easily change. You can certainly, one implementation of the ISA can be in order, and then the next implementation can be out of order. Next implementation can be, I don't know, taking everything and putting it into an FPGA, right, at a Dataflow. We'll see if that happens. So this is the contract basically. This is the manual. So what does that specify? I'm not going to go through all of this, but ISA specifies instructions, memory, how it's managed, how interrupts and exceptions are handled, how access control, priority, and privilege are handled, how I/O is handled, task management, power management, multi-threading support. There's a lot in this manual, and this is just volume 1. And this is also an old picture. So take it with a grain of salt over here. Microarchitecture, on the other end, is the implementation of the ISA under specific design constraints and goals. Anything done in hardware without exposure to software. And I put some things over here, but everything that I put over here, you could actually expose it to software by changing the interface. This is a contract, right? Actually, initial RISC machines, reduced instruction set computer machines, came up from the idea that what if we expose everything to the software? John Koch at IBM, when he developed the idea first, he basically said, I want to expose everything to the compiler such that the compiler can manage, software can manage everything that goes underneath hardware, like the control signals. Of course, that's very complex, right, at some level. But you could expose anything in hardware to the software. This is just, you just define the interface, right? Your interface may not be widely accepted once you do that, but having this radical thought frame like what he did at that time has changed how instructions have evolved over time also. Right? Okay, in order versus out of order, memory access scheduling policy. So some of these actually, as you can see, I have question marks. Caching, is it really fully microarchitecture? Not really today, because caches are exposed to the ISA via some instructions. You could do prefetching into the caches, for example. But some of the properties of the caching may not be exposed to the ISA, like associativity or replacement policy. Even size is not exposed, of course. If you know the size, you can do much better, but that's not exposed. That's not specified in that book, basically. People don't say, assume this cache size. It's specified in the hardware optimization manual, which is a completely different manual. It's not specified in the software, basically ISA manual, software developers manual. Okay, yeah, voltage and frequency scaling, error correction. I think you can think about that, whether that's part of the ISA or not. So this is just one example. I'm not going to go, well, maybe we can go through this in detail, but this is part of the ISA opcode, because that's exposed to the user. Number of general purpose registers, that's part of the ISA. The user needs to know. The assembly writer needs to know how many general purpose registers you have and how they're encoded. Number of ports of the register file, that's usually not part of the ISA, because that's internal. But in VLIW architectures, very long instruction word architectures, it could be part of the ISA. Some VLIW architectures make it part of the ISA so that the compiler can schedule instructions given the constraints of the functional units. Right? So it really depends on how you expose. If you don't know VLIW, take a look at the digital circuits course. Number of cycles to execute the multiply instruction, that's usually not exposed to the programmer. As a result, it's not part of the ISA, it's part of the microarchitecture, because programmer doesn't need to know about it to write correct programs, functioning programs. If they want to optimize it, yes, probably it's a good idea. But again, in the VLIW architecture, the architecture, basically what VLIW means is the software schedules the code and it makes sure the pipeline runs correctly. So if you have a multiply instruction, the software needs to know what instructions to schedule next in the next cycle, in the next cycle, in the next cycle, in the next cycle. If it doesn't know the latency of the multiply instruction, they cannot do that scheduling. As a result, this has to be part of the ISA that's exposed to the software. So it really depends on how you define the interface. Whether or not the machine employs pipeline instruction execution, again, this is not exposed in existing machines, most existing machines. As a result, it's part of the microarchitecture. Okay, I've already said this. So design points is extremely important in architecture. This is essentially a set of design considerations and their importance. This leads to trade-offs in both ISA and microarchitecture and system design. And as we discussed, there are many considerations: cost, performance, power consumption, energy consumption, and these are different things. Maximum power consumption determines your cooling or whether you burn when you keep something. Energy consumption is a completely different trade-off, right? Battery life or money. Availability, reliability and correctness, time to market, security, and you can keep adding. And design point is determined by the problem space or the application space, the intended users in the market, and hopefully that's obvious, right? Depends on what you're going to do with a particular computer. Right? If it's a device that's collecting data sitting in the camera somewhere, it has very different design constraints than a device that looks like this, which has very different design constraints than a supercomputer that's doing climate modeling and it wants to do it extremely fast. So this is the application space. I'm not going to go over this. This is from the reading that I mentioned by Yale Pat, but these are some of the applications. And there are many, many applications, and as we dream, they will appear. I have no doubt that people are creative enough to come up with many more applications. So the soul of computer architecture is really these trade-offs that are enabled by the design point. You have ISA level trade-offs. I gave you an example of it. Microarchitecture level trade-offs. I gave you a very small example of it, the adder, right? There are many different kinds of adders, and your trade-offs, which adder to use, depends on your application, how much parallelism you have, for example, your latency requirements, your energy, your power budget, your area budget, many, many things. And then system and task level trade-offs, how to divide the labor between hardware and the software. That's also important. What do you do in the software? What do you do in the hardware? What does the programmer do for you? That's also very, very important. That's part of architecture also. And as I said, computer architecture, actually, another way of thinking about it is the science and art of making the appropriate trade-offs to meet a design point. I think it's a more precise definition than what I said before. You're really using science, but it's also art. I think, unfortunately, that's the fact of life. Why is it somewhat art? Because things change. You don't really fully know the future. You don't really fully know what this thing will execute, really. Users, market, and they all change, actually. These things change over time. Users change over time. These things change. As a result, what you design, basically, you're designing today an architecture that will be useful for I don't know how many years in the future. First of all, it's not going to be deployed today. You don't know what the future would look like when you actually deploy the architecture, maybe 3 years from now, maybe 5 days from now, depending on what architecture you're designing. But after that, it's going to be deployed in the field for I don't know how long, maybe 10 years, 5 years. That again depends on your design point and goals. And we don't know what that future brings. Right? That's why it's partly art also. Of course, you can predict, you can use good science to predict all of those, but so far, we haven't figured out how to predict the future in science. As a result, it has to be somewhat art. And the future is not constant, as I said, right? Okay. So how can we adapt to the future? I think we should really discuss this before we finish. This is part of the task of a good computer architect. I think there are many options, bag of tricks, like keen insight and good design. I think these come with experience also, some of it, but I think having this keen insight and good design principles is really important. Fundamentals and principles, and using them. For example, for adapting to the future, heterogeneity helps. Reconfigurability certainly helps. Patchability, as we discussed in the last lecture, helps. Maybe there are other principles also. Okay, so we need to use basically many of these underlying technology better, as well as fundamentals and principles. And we covered a lot of this in digital circuits and computer architecture, just to give you an idea of how this fits. This is what we covered in digital circuits last semester. And if you really want to know about some of these, you should really watch the lectures. We're going to cover some of these again also, like caches, partially. But we covered logic design, Verilog, FPGAs, ISA, single cycle, microarchitectures, multi-cycle, multi-program, jogging your memory, pipelining, lots of things in pipelining. This is really the core of how to design a machine. Out-of-order execution, and different processing paradigms, which was fun, I hope. SIMD, VLIW, systolic, Dataflow, and we briefly covered memory, virtual memory, and caches. And these are the the execution paradigms that we covered, if you remember. And these are very fundamental. Don't forget these. I think it's very good, important for you to know them, but we're not going to cover them in this course. We're going to look at some of them briefly, maybe, but I think if you really not want to know, we should really study those lectures also, just because we cannot have the same course again, right? So I think I will recommend some things. If you're interested, you can review the videos, all slides and assignments. Everything is online. All of my courses are usually online unless there's a problem with the recordings. And particularly useful lectures for this course would be these, I think, if you're interested, pipelining and out-of-order execution. And definitely these. We're going to cover some of this, but I'm going to go through this relatively fast in the rest of this lecture after we take a break. And these are the basics. And these, even though these may span 1, 2, 3, 4 lectures over here, they're really shorter than that because they're shorter lectures, first of all, and they're part of the lectures over here. But I think it'll be very important for you to go over these because we're not going to cover caches fully, I think, unless some random thing happens and we change the direction. The data flow, right? Data flow is also very dynamic. And you can change the inputs to that data flow. Okay, basically in this course we will have more emphasis on the memory system, multiprocessing and multi-threading, reconfigurable computing, customized accelerators, So I think computer architecture courses need to adapt to how things change also. If I was teaching this course with pipelining and branch prediction and superscale execution, we could go into a lot of depth into those topics actually, but I'm not sure if it's going to be extremely useful for you afterwards. But I think that's why we need to cover the changing paradigms. And we also likely dig deeper into some digital circuits concepts. I think we've already done ISA, I'm not sure we're going to do more, but branch handling we'll cover because that's really fundamental, and also GPUs a little bit. This is a tentative agenda, but we may not exactly follow this order. We're going to look at memory quite a bit. Caches, as I said, we're not going to do a lot. This is actually an old slide. Main memory, we're going to cover a lot. Latency tolerance, prefetching, non-volatile memory, and emerging technologies, and some of these things over here. These I separate a little bit because this is the memory focus, and this is more computation and communication and heterogeneity focus. So hopefully it's going to be fun. And that brings me to my last slide, like 40 minutes later than I expected. Hopefully this was interesting. Okay, any questions, or shall we take a break right now? Okay, if you ask a question, you're delaying the break, so. Okay, let's take a break right now. Let's take a 15-minute break. Let's be back at 13:50.